All right, number one, it says find the third degree polynomial with real coefficients that have 3 and 2i as 0. So first of all, third degree tells you what about your answer? It should be x to the third. Good. Which is like an indication that what is there is not enough, right? What else do I know if I have a root that is 3 and 2i?
That's negative 2i.
Negative 2i is also one of my zeros, okay? So as soon as you see a complex root, something with an i, you automatically assume that its opposite or conjugate is one of the roots. So when I go to write this out, change my color, that's hard to read. I would get x minus 3, x minus 2i, and x plus 2i. And then I would always recommend foiling out the two that have your complex roots in them because the i's are going to cancel out if you do that correctly. You can use the shortcut on this one pretty easily. It's just the a squared plus b squared. So it would be x squared plus the b does not include the I, so it's just 2. 2 squared would be 4. If you forget the shortcut or you're unsure about it, you could always have foiled that out. But the same thing should have happened. The negative 2ix and the positive 2ix would cancel out. Then I got to FOIL with the x minus 3. So I'm going to distribute the x to both. I'd get x to the third plus 4x, and then distribute negative 3x squared, and negative 3 times 4 is negative 12. So I end up with x to the third plus, or sorry, let me put it in order, minus 3x squared plus 4x minus 12 equals f of x. So that's my completed polynomial. And should be raised to the third like it is. Questions on that one? Okay, then it said find the zeros of the function f of x equals x to the third minus 11x plus 150. First thing I would try to do is see if it's factorable, but you can't when there's an x to the third. There's not 4 terms, can't factor by grouping, right? So I have to go with all my possibles. I'm looking at the possible roots, which are plus and minus factors of the last over the first. There are a lot this time. 1, 2, 3, 5, 6, 10, 15, 25, 30, 50, 75, and 150. And I would try them. If you look, if you're using Descartes' rule, for example, it says that there are what? How many sign changes? 2. So it'd be 2 or 0, positive ones, right? And then if I do the negative, this would be negative. Plus 11x plus 150. How many sign changes? 1. So I would have gone with the negatives first. I'm not going to try them all because it takes all the way till we get to negative 6. That's the first one, okay? Negative 6. So just to save time, I cheated. I looked. It was negative 6. Okay, I could have also used a graphing utility to find where it crossed the x-axis, right? That's the same answer.
But on our test, we'd have to do.
They're not going to be that many on your test, but you would have to do the puzzles, yeah. Break. Tuesday.
Next Tuesday?
Yeah, a week from today.
That's the last.
That's our last.
And I don't see you Monday because it's a teacher work day.
So what she's saying is
So we should do it Wednesday.
Wednesday, we can go to her house and just have it in her room. Is it 25?
All right, so now obviously that's the one that worked, but we already knew that. Then I'm going to take what's left here, and this would now be quadratic. So x squared minus 6x plus 25. Still not factorable, but it's gotten to the point that my exponent is squared, which means I can use the quadratic formula. So negative b plus and minus square root of b squared minus 4ac all over 2a. A is 1, b is negative 6, and c is 25. So negative 6 makes that positive 6. Square root of negative 6 squared minus 4 times a times c all over 2 times a. 1, yeah, I don't know why I did that. I do know why, because I'm tired, but that's wrong. Okay, so now I've got 6 plus and minus the square root of 36 minus 100 over 2, negative 64 over 2. Take out the I, and then square root the 64, and I get 8i over 2. And these are both divisible by 2. 3 plus and minus 4i. So when it says solve, I need all the zeros, which includes the negative 6 from my synthetic and these 2 zeros at the end. You can leave them as plus or minus. Just realize that those are 2 answers, okay? You need both the plus and the minus. Yep.
So on the test, once you get like the first zero, it's not going to be factored
because they're complex roots. Right, which is the difference between quiz questions and these questions, right? The quiz, they were all real roots. On your test, they're not going to be real roots.
We'll have to do like completing a square or quadratic.
Yes.
Okay.
Somebody else hand over here. Yeah, good.
So whenever it's x to the third, you know automatically you're going to be finding all the zeros.
Well, it depends. You always finding all the zeros, but if it doesn't have 4 terms where you could factor it by grouping, then you're going to have to do your possibles. The rule is basically if you can't factor it and it's not quadratic, then you're doing your possibles. Okay, then I added this one on. So find the polynomial with the given zeros because I wanted you to do the binomial. So if I have a 3 plus 4i as a root, what else do you have? 3 minus 4i, which means my polynomial expanded would be or all the factors, x minus 5, and then x minus 3 minus 4i, and x minus 3 plus 4i. And then you want to start by distributing the ones that have the i's because that's where they're going to cancel. So I'm going to work with these two first. Go slow and cautiously. This is where silly mistakes get made, so just be really careful. Okay, this is x times x or x squared, x times negative 3, x times positive 4i, and then go to the next one. Negative 3x, positive 9, negative 12i, and then go to the last one. Negative 4ix, positive 12i, negative 16i squared. The I squared becomes a negative 1, so this becomes a positive 16. And then you want to make sure that the I terms cancel out. If they don't, then you already did something wrong. You want to check it now. So positive 4ix and negative 4ix cancel. Negative 12i and positive 12i cancel. I get x squared. Negative 3 is negative 6x. And then positive 9 and positive 16 is positive 25. Don't forget to bring down the x minus 5. Then I multiply x to the third, negative 6x squared, positive 25x, negative 5x squared, positive 30x, negative 125, x to the third, minus 11x squared, plus 55x, minus 125. Be really, really careful. It's super easy to make a mistake on those just because there's a lot of steps and a lot of sign changes. Questions? All right, so smart questions came up. So this one, it gave you the graph, right? Yeah. So it said, find all the zeros of the function, enter your answers as blah, 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 blah. Okay, so basically what I'm getting from my graph are my real roots. If you look at that graph, there are 2 zeros there, one at negative 2 and one at positive 2. If I take this function, because the middle term is x squared, this is actually factorable. It'd be x squared, and then minus 4 and positive 1. And then the x squared minus 4 can get factored further into the difference 2 squares. You can, it just takes longer.
Yeah, I think I got stuck in a different
Yeah, 2 and negative 2 should have worked. Did you have in your 0x to the third and your 0x?
Did I what?
Did you do a 0x to the third and a 0x?
Probably not.
Yeah.
Probably not. But I could have just looked at the graph and gotten the
Yeah, but you won't have a graph for your test, so it's good to know that you would have to factor that one.
Okay.
Yeah. And then you get negative 2, positive 2, and then x squared would equal negative 1. X would equal plus and minus the square root of negative 1, which is plus and minus I. So your 4 roots are negative 2, positive 2, negative I, and positive I.
For the question at the bottom, I didn't really understand.
So it says, is there a relationship between the number of real zeros and the number of x-intercepts? The answer is yes. All your x-intercepts are real zeros.
What about the
So the i's won't show up on your graph. Does that make sense? Yeah. So the 2 and the negative 2 were on the graph, right? But the i's you don't see on a graph because they're imaginary. Sure. All right, so 2, 6, and 2, 7 I put together. These are graphs of rational functions. So it's a lot of new stuff, but then it mixed in is like the solving of the roots and that kind of stuff. So these are graphs. These are not graphs you're going to use a graphing utility on your test for, but I will show you how to use a graphing utility to check answers, okay? You are basically going to be able to graph things that look really, really strange. They're going to have like asymptotes, vertical, horizontal asymptotes. Tomorrow we're going to get a slant asymptotes, which is what the 2, 7 part of this is, okay? So we start with like, what is a rational function? A rational function is just one that can be written as a fraction. So all of these graphs will be written as a fraction. They could be something as simple as like 1 over x, or it can be something that's both factorable in the numerator and the denominator. So the goal here is to, and I'll take you through the multi-step process, but find all the asymptotes and then whatever points we can get from our intercepts, and then at the end plug some points in if we don't know what it looks like, just like we used to do. So quick review on domain. We've done this so many times, okay, but you need to know it for these. The domain of a function is all real numbers except if one of these 3 cases happen. If there's a variable in the denominator, we'd set the denominator not equal to 0. If there's a variable under square root, we set whatever's underneath the root greater than or equal to 0. And the combination of that if there's a square root in the denominator. Really, for this section, you're only going to see the variables in the denominator, okay? But just know that obviously those still exist. We just don't have to do them. You're not going to see square roots in the fractions.
So we don't really have to worry about the other 2.
You won't see them. You just won't see a square root in the questions. So this one just says, find the domain of the rational function. So I'm only looking at my denominator because it doesn't matter if the x in the top is 0, right? But my denominator cannot equal 0, which means x cannot equal 4. So my domain is negative infinity to 4, union 4 to positive infinity. All real numbers except 4. Now what you'll notice is this is actually a simplifiable equation. I could factor the top, right, difference of 2 squares, and cancel it out, which is going to affect our graph, but it does not affect our domain. From domain, we go from the very beginning before we cancel anything out, because eventually we're going to train ourselves to look to see if we can cancel something out. It's important. It causes a hole in our graph. But for domain, you look at the beginning, okay? And again, always the denominator. All right, so what can I do here? Good. You can. Not equal. Okay, you could have also factored it into the difference of 2 squares, right? So this would be negative infinity to negative 6, union negative 6 to positive 6, union 6 to positive infinity.
So it's everything but those numbers?
Yep. Because those numbers would make my denominator 0, and we divide by 0, what happens?
It's not.
It's undefined.
The last one is what?
6 to positive infinity. So if you have a 2 not equals, it's negative infinity to the smaller one, smaller to bigger, and then bigger to positive infinity. Okay, so we're going to start these using transformations. So these goes back to the beginning of chapter 1, okay? When we did a transformation with a reciprocal function, which is what this is, my original graph is 2 little curves in the top right quadrant and the bottom left quadrant. That is the parent function for 1 over x. So if we add or subtract in the function, it does our horizontal shift, right? So this is actually a shift to the left 3 units. So we would take our asymptotes, which are happening at 0 on the y and 0 on the x, and we shift everything to the left 3 units. So instead of my asymptote being on the y-axis, it's over here. Still asymptote on the x-axis. So my curve comes through here and here. So we are going to get way more specific than this, but the general idea behind the transformation should still help you out. Okay, look at the second one. What's the minus 2 in the bottom doing? Right 2. How about the plus 1? Up 1. So my asymptotes that were at 0 and 0 are now shifted to the right 2 and shifted up 1. And then you draw your curves.
So it has to be like on the other side of that.
For the, well, I mean, this, we're going to do a whole bunch more to this stuff, but for these, yeah. Okay, so the vertical asymptotes, again, think vertical, so up and down, right? The vertical asymptotes of my parent function are the y-axis. So this would be x equals 0. That's where my vertical asymptote comes from. But as soon as I start moving this function around, as soon as I start transforming it, that's going to get shifted, okay? And it comes from the opposite of my domain. So if my equation said 1 over x, what would be your domain restriction? X cannot equal 0, so x equals 0 is where my vertical asymptote is. Your asymptote is where the x cannot be, okay? So it's the exact opposite of your domain. That asymptote is like something that makes my function undefined. So it cannot touch that line. It gets as close to without possibly touching that line as it can because it gets teeny, teeny, tiny like the lower you go. But it cannot touch that line and it can't cross through that line for the vertical asymptote. So the x cannot equal 0 is your domain. The x equals 0 is your asymptote. Your asymptote is where it can't be, if that makes sense. It's where your x can't be. So you're going to see like notation like this. I'm not testing you on this notation. I don't need you to stress out about it. But when you see like the book will try to explain your graph using this kind of notation. If it says x arrow a plus, it means x as it's approaching a, which would be a value. Okay? Positive means from the right. So it's coming in from the right. What's happening there? That's all. Okay? If it was minus, it's saying x as it approaches that number from the left. If I'm doing x to positive infinity, this means that it's going to be increasing. Okay? Without bound, meaning it doesn't stop. And x is approaching negative infinity, means it's going to continue to decrease. And again, without bound. This is why you see that kind of notation. So on this graph, this is f of x equals 1 over x squared. So what happens when we have x squared is that they both flip to be up because you'd only have positive values. So they're going to happen in the top, like quadrant 1 and quadrant 2, the top right corner and the top left corner, okay? And this notation, and again, I don't want to get hung up on it. I'm not going to spend that much time on it because it's not like something I'm going to test you on. But just so that you see it, is basically saying as x approaches 0 from the left. So my x values are left and right. As my x gets closer and closer to 0 from the left-hand side, my f of x, which means my graph, is getting bigger. It's approaching infinity. So it means as this curve starts to come in here, the closer I get to my y-axis, the bigger the values are, okay? This on the right-hand side says as it approaches 0 from the positive side, so from the right side, it's also approaching infinity. So as this curve comes this way, the values for f of x are just going to keep getting bigger. That's what that means, okay? It goes in and up without bound, okay? So that's, again, don't freak out about the notation. It's just that you could read a graph like that. We are going to go much more structured than that. We're going to start with the asymptotes. So for vertical and horizontal asymptotes, because you're going to find both, the line x equals a, which means x is going to equal a number. This has to be a vertical line, so it has to be an x equals, just like your axis of symmetry had to be an x equals. The closer it gets to that line, the bigger or smaller the values of f of x are going to be. So it just means it's getting close to that line, as close as it possibly can without touching it. The horizontal asymptote is a y equals a number, because it's a horizontal line. So asymptotes have to be lines, have to be in equation form. Here's just some examples of what they could look like. So the one all the way on the left has 2 vertical asymptotes, and it actually has a horizontal asymptote. Now this was what's weird. Graphs can cross a horizontal asymptote. They cannot cross a vertical asymptote, but they can cross a horizontal asymptote. The horizontal asymptote, if it's divided into 3 parts, the middle can cross through it, but what it's doing on the outside is affecting where those curves are going. This is always going to get close to without touching the outsides. But in this graph, the inside does cross it. It is possible to cross through a horizontal asymptote, but it cannot cross through a vertical asymptote.
Those green lines aren't touching though, right?
The green, no.
So horizontal can and vertical cannot.
Correct. Vertical is literally undefined. Horizontal is like a guide. The next one has a vertical asymptote here, and it's got a horizontal asymptote here. It actually has a hole in this graph, which we're going to talk about in a little bit. And the last one has no vertical asymptotes, okay? There's no way to make x squared plus 9 equal 0. So that won't have, like, if you're going to graph this on your test, you're going to have at least a vertical asymptote and a slant, or a vertical asymptote and a horizontal, but we'll get to those.
Wait, you said the second one has vertical and...
Yeah. And this time the horizontal doesn't cross. But then it actually has a hole. Again, we're going to talk about that later, but it has a hole. All right, I'm going to skip this. I'm going to go straight to here. So there are 3 cases for, actually, let me start with vertical. There's the vertical asymptote is the one we talked about already. The vertical asymptote occurs when the denominator equals 0. So I will literally take whatever's in the bottom of my fraction, I will set it equal to 0, I will solve, and that's where my vertical asymptotes happen. For the horizontal asymptotes, there are 3 cases. Now this is referring to n and m. N is the highest exponent of the numerator, and m is the highest exponent or degree of the denominator. Okay, so think n numerator, m denominator. If n is less than m, so if the highest exponent in the top is less than the highest exponent in the bottom, then my horizontal asymptote, yeah.
I can't see that.
It just says numerator and denominator.
No, like the slide.
So highest exponent in the top, less than highest exponent in the bottom, and you have a horizontal asymptote at y equals 0.
You don't need that.
No. If they are equal, if the highest exponent in the top is the same as the highest exponent in the bottom,
What does it say?
if n equals m, then the horizontal asymptote occurs at y equals the leading coefficient of my numerator over the leading coefficient of my denominator. What's leading coefficient mean? The number on that highest exponent. So the number on the front of the one that has the highest exponent. That's if the exponents are the same, okay? The third case is if the exponent in the top is bigger than the exponent in the bottom, there's no horizontal asymptotes. There could be a slant, which we'll get to, but there's no horizontal. Directions here say find the horizontal and the vertical asymptote, if any, of the graph of the rational function. So we're still not graphing yet. We are just finding vertical and horizontal. So I start vertical. Vertical is from your denominator, okay? Vertical comes from setting your denominator equal to 0. How do I solve x squared minus 36? I can add the 36, square root, making sure plus and minus, or
What is the V?
vertical asymptote. I can factor it. The benefit of factoring is that later when we're looking for holes, we're going to have to factor it anyway, so you might as well just start factoring it, okay? So I would factor this out as x plus 6 and x minus 6. So I have 2 vertical asymptotes. One at x equals negative 6 and one at x equals positive 6.
So the domain.
Domain is the opposite, right? So domain says it can't equal negative 6 and it can't equal positive 6. Horizontal asymptote. To figure out my horizontal asymptote, I have to look at what's the highest exponent in the top, what's the highest exponent in the bottom. So highest in the top is 1, highest exponent in the bottom is 2. So if you need the cheat sheet, go back. What happens when the exponent in the top is less than the exponent in the bottom? Y equals 0 is my horizontal asymptote. Okay, go to B. Vertical asymptote. How do I get it? Good. Factor it. Set it equal to 0. So I have 2, x equals -2, and x equals +2. Horizontal asymptote. Look at the highest exponent in the top. It's what? 2. Highest exponent in the bottom? 2. So they're the same, right? When they're the same, we do the leading coefficient of the top over the leading coefficient in the bottom. What's the leading coefficient in the top? 3. What's the leading coefficient in the bottom? 1. So y equals 3 is my horizontal asymptote.
You have to add the y equals.
You have to. It's a line.
Would you accept for the vertical asymptote x equals plus or minus?
Sure. Yep. You could start it. Yeah, yeah.
It's not factor 1.
Then what? Is there any way to make that 0?
Yeah, you can subtract the 1.
And then what?
And then make it high.
Is I on your graph?
So there's
Do not make it I. You can't, right? There's no way to make this 0. It would get x squared cannot equal negative, or equal, sorry. I'm thinking domain.
Oh, so we can't have eyes.
Nope.
Yeah, because that's not graphable.
You can't graph that.
So,
How about horizontal asymptote? Highest exponent in the top is? Highest exponent in the bottom? 2. So top bigger, top less than again, y equals 0. All right, so this is what could happen, and this is where it gets really tricky, is because if I can simplify it from the beginning, first of all, you have to, after you find your domain. So if we're going to do this in steps, we would do domain, then we would do test for holes, and then we would do what we just did, which is vertical and horizontal asymptotes. If a factor cancels out from the bottom of my fraction, then there is no longer an asymptote there, but there is a hole. So you literally get an open dot on your graph. It would look like this. They call that a hole. It's a hole, right? And you would find it by literally plugging back in that value. So if I take, for example, this one that's here, and I can factor my numerator, right? Because we can factor that numerator. So it would look like this. And in doing so, get to the point that I can cancel something from the top and the bottom, which is what's happening here. Then there is a hole at x equals 2. To find the exact point, we take the 2 and we plug it back in. Take the 2, plug it back in to my simplified equation. And I'd get 2, 4. So 2, 4 is the exact location of the hole.
Can you explain that last step again?
Yep. So when you cancel, right, whatever value of x is gone. It got eliminated. There's a hole there. So we take that value of x and we plug it into our equation after we've simplified it. And that's the exact location of your coordinate point.
Okay,
So if I had y squared, nope, not y squared, sorry, x squared, minus 9 over x plus 3. Let's say that's my f of x. I can factor the numerator, right? X plus 3.
Why are you even looking at the numerator?
Because you have to find your holes.
Oh.
Yep.
So you have to do that no matter what.
So like for just asymptotes, no, but it will start, we're going to start to put it all together. Yep. So this would cancel, right? Now, this is the factor that canceled out. So I would set that equal to 0, and I would get x equals negative 3. That's the x coordinate of my hole. And then I would take and plug it into my simplified equation. And that's the y coordinate of my hole.
So it's negative 3 over 6.
Yep.
That's where the hole.
Yep. And I canceled this out, which really means that this is what's left of my equation. What kind of graph is that? That's just a line. But it would have a hole at negative 3, negative 6.